The Earth is like a mosaic, constructed by different parts that are always moving, changing its form, colors and sound, sometimes in a very enigmatic way. These mosaic pieces are connected by a force that we cannot see, touch or feel, but is everywhere, around us, around the Earth, and more. It extends from deep inside the Earth to outer space. We present to you our planet's magnetic field. You might think, why is that useful to me? Well, the Earth's magnetic field is acting like a shield. It protects us and our satellites from harmful particles coming from the sun and deep space. Without the magnetic field, forget about the internet, social media, online meetings. But do you know where our planet's magnetic field is produced? We are 10 female scientists from 10 different countries around the world. We invite you for a scientific journey from the core to space. I'm Sanja Panowska, a researcher at GFZ Potsdam, and I will lead you through this amazing journey. Let's start from very deep inside the Earth. The majority of magnetic field at the surface is produced in the Earth's outer core, which is almost 2,900 kilometers under our feet. Well, if you were to travel in a straight line from where our researchers at GFZ Potsdam are based, then we could be in Cairo, Egypt. Or it's the same as driving a long, tiring 28 hours along all the wiggly roads to Lisbon. Imagine traveling this distance in the direction of the center of the Earth. Actually, we cannot. The deepest we have dug into the Earth was about 12 kilometers. That is more or less a third of the distance between GFZ Potsdam and Berlin, a short 40 minutes drive. You might ask, how do we know about the existence of the Earth's core if we have traveled less than 0.5% of the way there? It was actually a Danish geophysicist named Inge Lehmann who discovered that the Earth has a solid inner core. How did she discover that? Let's invite Kuan Yu to answer this question. Kuan Yu is from Taiwan. She did her bachelor's in Earth Sciences in the National Central University in Taiwan. Then she did a master's degree in exploration geophysics in the Institut de Physique du Globe de Paris in France. Recently, Kuan Yu moved to Germany to do her PhD in the seismology group at GFZ.
Have you ever thought how scientists can understand the Earth's interior? You might think we can know the Earth's interior by drilling. However, even the deepest holes we can drill so far is Kola, but it's only 12 kilometers. If we cannot drill lots deep, how can we know the Earth's interior? Instead of using these direct methods like drilling a hole, we can use seismic waves to study Earth's interior. When an earthquake occurs, it generates seismic waves which propagate through the different layers and different material of the Earth's interior. When these seismic waves reach the ground surface, it can be recorded by station or we say seismography. This recording, which bring the information from the subsurface, are called seismograms. When we look at this seismogram, we can find there are seismic waves at different velocity and different amplitudes. There are two types of waves, surface wave and body wave. Surface waves travel through surface, while body waves travel through Earth's bodies. Body waves can travel through the deeper parts of the Earth, so it's mostly used to study the Earth's interior. There includes two types of body waves, P wave and S wave. P stands for primary wave because it travels fastest, while S stands for secondary, as it travels slower than P wave. P wave travels through the subsurface like pressure wave, as their particle motion is parallel to the direction of wave propagation. P wave can travel through liquid and solid. When P wave travels through liquid, it's slower than when it travels through solid. S wave acts differently than P wave. S wave is a wave its particle motion is perpendicular to the direction of wave propagation. S wave can only propagate through solid. So now we have this basic concept about seismic waves, and we can use this information, try to know the Earth's interior, and then build a simple model. The well-known seismic velocity model is Planck model, which consists of 4 layers: crust, mantle, outer core, and inner core. If we look at the Planck model, we can find the S wave velocity is 0 in the outer core, and P wave travels slower in the outer core. So based on the information we had before, we can infer that the outer core should be a liquid layer, and the outer 3 layers, crust, mantle, and inner core, should be the solid layer.
Okay, we know that earthquakes do not only cause big troubles for humans, but can also be used by scientists to learn about the deep Earth. Now we have the question: how exactly does the Earth's core produce the magnetic field? Let us invite Monika Korte to tell more about that. Monika Korte is from Germany. She graduated in geophysics in Munich. Her PhD was at GFZ Potsdam and Freie University Berlin, followed by 2 postdocs, one at GFZ Potsdam and one at the Scripps Institution of Oceanography in California, USA. Now Monika is a researcher and also interim head of the geomagnetism section at GFZ Potsdam. She is also a Secretary General of IAGA. IAGA is an international organization aiming to bring together groups of scientists studying different aspects of the magnetic field.
The largest part of the Earth's magnetic field is created deep inside the Earth, in the Earth's outer core. The Earth's outer core is fluid and is mostly made of iron, which is electrically conducting. And also it is constantly in motion. There are fluids in Earth's outer core that are probably largely driven by heat, by the Earth cooling down over Earth history. And so the movement of these fluids, iron in the core, together with the influence from Earth rotation and the presence in Earth's magnetic field, creates a dynamo effect that sustains the magnetic field and sort of keeps creating it all the time. Because the Earth's magnetic field is created by dynamic processes in the core, it is also not constant but keeps changing all the time. And most of the time these changes are moderate and slow. But over Earth history there were several times when the magnetic field completely reversed its polarity. And these events are called polarity reversals if they happen in a way that you have a stable field in one polarity, then you have a reversal, and then the field remains stable in the other polarity. The reversals happen several times over Earth history, but they do not happen at fixed time intervals. But there were time intervals where reversals occurred every few 100,000 years, but there were also time intervals where the field was stable over millions of years. There's a very interesting question when the next reversal or excursion will occur, and unfortunately we do not really know. We do not understand these dynamo processes in the core in so much detail that we really have models that can predict the future of the Earth's magnetic field over tens of years or decades. And what we certainly can say that the next reversal will not happen in 1 or 2 years or in 10 years, because just from the physics of the process it cannot happen very quickly. It is certainly a process that takes at least several hundred years, probably a few thousand years, maybe even several thousand years. The influence on humans and on life on Earth is a more difficult question because the influence from the direct increased radiation that hits the Earth is still shielded by the atmosphere on the Earth's surface. So there should be no direct influence from the increased radiation there. Of course, also processes in the atmosphere might change from the increased radiation that enters there, and that might, especially because it's on the time scales of these hundreds or thousands of years, might have an influence on the environment, the climate. I think the influences of reversals and excursions is still a field that needs further research and has many open questions. There are some papers, but also some controversial papers that predict strong effects from the last excursion that happened 41,000 years ago, the Lachamps excursion. But also there are several studies that see no correlation between mass extinctions of organisms and magnetic field reversals, which one might also think could be correlated if there were strong environmental effects of reversals. So I think that is an interesting question for further research.
Imagine that! The magnetic field changed polarity many times in the Earth's history. But how exactly do we know that this really happened? That is a question to Tatiana Savranskaya. Tatiana Savranskaya comes from Russia. She got an engineering degree at Human State Oil and Gas University. After she did a double master's degree in reservoir geosciences and engineering at the Institut Français du Pétrole in France and Human State Oil and Gas University in Russia. She recently finished her PhD in geophysics at the Institut de Physique du Globe de Paris, and now she works as a postdoctoral researcher at GFZ Potsdam with a Humboldt Research Fellowship.
Earth's magnetic field is restless. We know that it has been flipping in the past several times from independent methods. In the early 20th century, French geologist Bernard Brun analyzed basaltic lava rocks and argillaceous sediments and discovered that the polarity captured by rocks is opposite to the present field polarity. In 1920, Japanese geophysicist Matsuyama analyzed rocks covering early Pleistocenic age, spanning between 2.6 million years and 11,000 years before present. He confirmed that rocks were carrying different polarities. Independent methods telling us that Earth's magnetic field was flipping in the past relies on seafloor spreading. This process takes place on the ocean mid-ridge, where continental crust is formed through volcanic processes. So when the lava is erupted and continental crust is formed, it records the present Earth's magnetic field polarity. Afterwards, it spreads away from the ridge. In the middle of 1960, high-precision magnetometers were developed, allowing us to measure these anomalies on the seafloor. This is a direct method of Earth's magnetic field changes observation. We can also rely on the indirect method for studying Earth's magnetic field, such as archaeomagnetic samples and natural geological samples, for example, marine sediments, lake sediments, or lava rocks. Marine sediments contain tiny magnetite particles that orient themselves according to the magnetic field lines in the water column and in the sediments before being compacted and locked. But the problem that magnetization of the rock is a complex function not only of the strength of Earth's magnetic field, but also it's a function of concentration of magnetic minerals in the sediments.
So we know more about our dynamic mosaic. The liquid in the outer core is always moving and producing the Earth's magnetic field. We know from old rocks and sediments that this field changed polarity many times in the Earth's history. But between the core and the surface, there is a very thick layer of the Earth, which is called mantle. Can you imagine how are the interactions between the lower part of the mantle and the core? Priya Roy will explore this important part of our mosaic. Priya Roy is from India, and her bachelor's was in geology at Presidency College, Kolkata. Staying in Kolkata, she continued her studies, doing a master in applied geology in the Presidency University. Then she did another specialization in earth sciences at the Indian Institute of Science. Now she is a PhD student in the geodynamic modeling group at GFZ Potsdam and will tell us more about the lower mantle.
The region from 660 km to 2900 km below Earth's surface is known as the lower mantle, and this represents 56% of total Earth's volume. And the rocks in the mantle can flow with geologic time scale. So we can simulate the convection pattern of the lower mantle. Lower mantle contains two continental-sized blobs beneath Pacific and Africa, and these structures are very unique in terms of their composition and dynamics. When seismic waves pass through them, the waves slow down significantly. So scientists have proposed that these regions can be a representative of primordial earth material which didn't deform over time and can be acted as a potential plume generation zones. This kind of large scale structures can make the lower mantle a bit more challenging zone to better explore. In 2002, a high pressure experimental study revealed that there is an occurrence of phase transition from perovskite to post-perovskite at the lowermost part of the mantle, which is around the bottom 300 km of the mantle. And this post-perovskite is a high pressure polymorph of perovskite, and when post-perovskite forms from perovskite, it generates heat, and this heat generates a more efficient convection pattern at the mantle, which ultimately leads to the quicker growth of continents at the surface. Also, this post-perovskite having a very ordered structure can deviate seismic waves in different orthogonal directions, which makes lowermost mantle seismically anisotropic. And also post-perovskite may contribute to strengthen the Earth's magnetic field, which shields the dangerous UV rays or the cosmic rays and made our planet Earth possible for life.
Certainly, we see that the lower mantle has a great influence on the core and also on how the magnetic field is produced. Since our dynamic Earth is all connected, how does the core connect to the Earth's surface? Let's ask this question to Elodie Kendall. Elodie Kendall is British. She studied physics at the University of Warwick in the UK, followed by a master's in geophysics at the University College London, where she did her PhD in computational geophysics. Today, Elodie is a postdoc with the Geodynamic Modeling Group at GFZ Potsdam.
And today I'm going to be talking to you about mantle dynamics and this connection between the Earth's core and the thin outer layer. And so this mantle, the mantle of the Earth is roughly 3,000 kilometers thick, and it's actually very difficult to probe this very deep, very thick layer right beneath our feet. And so to probe such deep structures, what we must do is piece together indirect observations from different fields such as seismology, so the study of earthquakes, geochemistry, geodynamics, geology, and so on. So to conduct the huge amount of heat that is emitted from the core, the mantle acts a little bit like water in a stove, and what it does is it convects. And so actually this less dense material is rising and more dense material is falling. Now this was proposed by Arthur Holmes in the 1920s. And so actually, although the mantle is a solid, if it's hot enough on the timescales of millions of years, it actually flows. It was then proposed in the 1960s that this convection is actually hindered close to the surface, and it's hindered by these rigid so-called tectonic plates. And actually these are very cold plates with respect to the ambient mantle, and so they really form this like lid on the convection of the mantle. And so when we think about the position and the heights of the continental and oceanic plates, we really realize that these plates determine global oceanic circulation, and then they can affect the climate as well. And so that really makes us think how important plate tectonics is for life on Earth, but also how important it is within our solar system and how unique it is. So where the plates actually move past each other, we can actually have very large fault systems forming, such as in California at the San Andreas Fault. The plates can also spread apart where mantle is upwelling beneath them. And what we can also have is where the tectonic plates actually colliding head-on. So in one case we have a continental plate, in which case material gets shunted onto the plate, and we can actually get huge mountain belts forming, such as in the Alps or in the Himalayas. Now, on the other hand, if there's an oceanic plate colliding, it's normally subducting under the opposing plate. And this subduction is really forming the downwelling part of convection in the mantle. And often volcanism ensues at the surface of these regions. So it's expected that volcanoes form around the boundaries of these plates. However, in the 1970s, scientists were puzzled to find volcanoes erupting in the middle of the plate, such as at Hawaii. And so actually Jason Morgan proposed that the culprit of these, the surface expression, the volcanoes, was actually hot upwelling mantle rocks, and we call these structures mantle plumes. And so you can think of these structures similar to the structures you see in your lava lamp at home, so these kind of mushroom-shaped features. And actually these features form the majority of the upwelling part of mantle convection. So we've now really seen the whole upwelling and downwelling parts of this mantle convection. And so to conclude, the Earth's mantle comprises a whopping 84% of the Earth's volume, yet there are these large-scale processes that can connect the Earth's core all the way up to the Earth's surface and vice versa.
After traveling a long way through the mantle, the magnetic field finally arrives at the surface. Remember, we learned that information about the magnetic field in the past is captured in rocks and sediments. What about the magnetic field today? Let's ask this question to Cathie Pinero. Cathie Pinero is Brazilian. Her bachelor's was in oceanography from the State University of Rio de Janeiro. And in the same city, she did her master's in geophysics at Observatorio Nacional. She did her PhD at ETH Zurich, Switzerland, and then a postdoc at Université de Nantes in France. She is a researcher of Observatorio Nacional in Brazil. This year, she is working as a collaborator at the Nîmes Magnetic Observatory in Germany, where we are going to meet her.
We actually know that the geomagnetic field is varying now because we can measure it directly by observatories and satellites. Magnetic observatories are fixed locations around the globe that measure the magnetic field for long periods. Usually we measure the data at each second with a very high precision. These observatories have to be in isolated locations, far from artificial disturbances, as it is the case of the Magnetic Observatory of Nîmes, where I am now. Another example is Tatuoca Magnetic Observatory, located in Brazil in a small island in Amazon. Since this observatory is very isolated, we are free from magnetic disturbances, and then the data has a very good quality. The problem is that magnetic observatories are not equally distributed around the Earth's surface. So satellites complement this data of magnetic observatories and provide a very good spatial coverage. One example is SWARM mission of ESA, which was launched in 2013 and provides valuable data since then. By joining data of observatories and satellites, we can construct global models of the geomagnetic field varying with time. The GU-FM1 model includes historical data and presents the evolution of the geomagnetic field over 400 years. Note this red region of weak magnetic field intensity that is increasing and moving from Africa in direction to South America. This region is called South Atlantic Anomaly. The South Atlantic Anomaly is the region at the Earth's surface where the geomagnetic field is the weakest. Therefore, the shield provided by the geomagnetic field is also weaker in this region. As a consequence, cosmic rays penetrate the atmosphere and can cause serious damages to telecommunication systems and aerospace activities. There are more recent models showing that this anomaly is splitting in two regions. The interesting thing is that the observation of this anomaly is a very important clue to find out how it is produced at the core mantle boundary. The majority of the geomagnetic field is produced in the core. However, there are other parts from the crust, induced and external fields that we also record at magnetic observatories and satellites. Therefore, the data from magnetic observatories and satellites can be used in a variety of studies from the core to the space.
I see. So the magnetic field that we measure in observatories and satellites does not come only from the core. It is only a part of the magnetic mosaic. Where does exactly this external magnetic field come from? Let's talk to Sajjad Sobkhis to discover more about the magnetic field in space. Sajjad Sobkhis is from Iran. She graduated in geomatics engineering at the Babol University of Technology. In Tehran, she did her master's in geodesy at KN-Tuzi University of Technology. Now, Sajjad is doing her PhD in ionospheric variations in the geomagnetism section of GFZ Potsdam.
Up above the clouds in the sky, the atmosphere begins. A very active part of atmosphere that absorbs a lot of energy from sun is called ionosphere. We call it simply ionosphere because it consists of ions that are basically atoms and molecules that have been electrically charged due to solar radiation. Since the sun radiation mainly forms ionosphere, the night side of the Earth has less ionization than the day side of it. Depending on the amount of energy that ionosphere receives from sun, its density will change. And any change in ionosphere will influence the satellite communication, radio communication, and navigation systems such as GPS. Therefore, it is very important to understand the variations of ionosphere. Earth's weather dynamics, such as hurricanes and winds, can influence ionosphere. Also, several solar phenomena, such as solar winds or geomagnetic storms, can cause variations in the ionosphere. Well, we know that Earth's geomagnetic field is constantly changing, and this is partly due to the perturbations in the Earth's ionosphere, which also can vary depending on local time and geographic latitude. As I said, there are many free electrons and ions in the ionosphere layer, and this is why this layer is electrically conductive. The electric currents flowing in the Earth's ionosphere will cause daily variations in the Earth's magnetic field, which is called solar quiet. This solar quiet system is very much sensitive to the interactions between the sun and the Earth, because as the solar radiation increases, the amount of ionosphere's conductivity will increase. So, as the Earth daily rotates around itself, we can see daily variations in solar quiet. And obviously, as the Earth rotates around the sun throughout the year, it will change its position and angles facing the sun. So we clearly expect a seasonal variation in solar quiet. In general, diurnal geomagnetic variation can be caused by both external magnetic field variation or induced variations. This induced magnetic field originates from conductive Earth. For example, earthquakes can cause changes in Earth's conductivity, and as a result, they will cause changes in induced geomagnetic field. On the other hand, any ionospheric disturbances, which are mainly due to solar radiation, can cause changes in the external field. And we know that this external field variation is dominant. Therefore, studying geomagnetic perturbations using the data from observatories or satellites is very important. It will help us to better understand the physical process in the Earth's ionosphere and near-Earth space, which are necessary to better understand the climate and space weather.
Going further away from the Earth's surface, we find the magnetosphere, where the Earth's magnetic field extends and protects us from harmful energetic particles. This dynamic region of our planet completes our mosaic. The invisible force, our magnetic field that comes from the core, interacts with the magnetic field that comes from the Sun. Can you imagine how it happens in space? Have you heard about magnetic storms and the effects they can cause on our technological life on Earth? The next piece of our mosaic will be discovered by two scientists, Marina Garcia Peñaranda and Julia Himmelsbach. Marina Garcia Peñaranda is Spanish. She graduated in geophysics at the Universidad Complutense de Madrid, where she also did her master's degree in seismology. Today, Marina is doing her PhD in space physics and space weather at GFZ Potsdam. Julia Himmelsbach comes from Austria. Her bachelor's was in technical physics at Vienna University of Technology, where she also did her master's. Now she is a research fellow at GFZ Potsdam and works on numerical modeling and simulations of radiation belt physics.
The magnetosphere is a region around the Earth. In space it is dominated by its magnetic field. It looks like a bubble in the shape of a comet and actually shields the planet and protects us from the harmful radiation coming from the Sun. These constant particles like streaming off the Sun, it's what we call solar wind. The solar wind is like usually really constant and nothing bad happens. However, there can be like really extreme events of like incoming particles and explosions of particles that can actually modify the solar wind pressure and actually hit the Earth. Usually it's this event it's what we call geomagnetic storms. The geomagnetic storms are usually a really mild event and they manifest as auroras that can be seen from high latitudes.
Changes in the ring current are responsible for the global decrease of the Earth's magnetic field, also known as geomagnetic storms. The ring current is a toroidal-shaped electric current carried by charged particles at distances between 3 and 5 Earth radii, measured from the center of the Earth. The disturbance in the Earth's magnetic field during a geomagnetic storm is proportional to the total energy of the ring current particles. The ring current particles originate either from the solar wind or the terrestrial ionosphere.
Sometimes we have like really extreme events. For example, there's the Carrington event that happened in the 1800s. And it was actually the biggest geomagnetic storm ever recorded. It actually burned all the telegraphy systems. There was also auroras that could be seen from the Iberian Peninsula, and this is a really kind of crazy thing to happen. And this is because if that were to happen today, our society relies too much in the internet and the electricity power grids. A really huge geomagnetic storm could actually produce a huge blackout because the induced currents could actually destroy all the power grids and like leaving like huge cities, maybe even countries without electricity for days. Also, the satellites communication would be down, so air traffic control, internet, everything would be down. So this could actually affect to the most important things such as hospitals, communication, and daily life, because there would be like no money. What do you do with no money? No WhatsApp, no internet, no Twitter, no nothing. And that's why we really need to study the magnetosphere and how it works to be able to predict and protect us from those harmful situations.
I hope you enjoyed our scientific journey. Our story is over, but the magnetic mosaic is far from being complete. Every day we face new questions, challenges that lead us to discover amazing pieces of our incredible Earth.